Hey people, so in this video I will try to show conditional statements, how to access block groups, and using booleans to indicate states in your code. To do this I have made a solar panel on some rotors which I want to get to align to the sun. After that I'm going to expand on that idea, adding some solar panels. So yeah, this is a basic setup, solar panels on two rotors. I have named them pivot rotor and base rotor. So yeah, let's get to it. So I have input the blocks as per the last video, and now I gotta do some logic. So I'm gonna use primarily boolean values as I mentioned in the last video, so values that can be true or false, and if statements. The way an if statement works is if, well, the way it's constructed is if, parentheses, and then some curly braces on the end, where you can press enter and it'll move down. So how it works is if this is true, then we do this. So the code between these curly braces will only run if whatever we put in here is evaluated as true. So you can't just put a value like 5 or 45. You have to say, for example, if, I don't know, 5 is less than 1, then this code runs. And it will never be less than 1, so this code will never run. How I want to do this is I want to first pivot the solar panel. I want to align it vertically, and then I want to rotate it. So I need a way to tell my code if my solar panel is pivoted in the correct orientation. So I'm going to make a boolean. I'm going to make a bool called pivot aligned. And I'm going to set it to false in the beginning because we're going to assume that it is not aligned to begin with. But as I said, this code will only run if it evaluates as true. And well, this is false. We're not aligned. We want to run the code if it is not aligned. So what we can do is we can make an exclamation point at the beginning. That basically means not. So if pivot aligned is not true because of the exclamation point, then we run the code. So whatever in here will be run as long as the pivoting is aligned. Next up, we are going to assume that we are going to start off with a totally offline system, so the rotor is not running. So we need to get that running, but we don't want to, since we want it to change direction, depending on how it's moving against the sun, we only want to turn it on once, or we only want to turn it on if it's actually off. So we're going to make another boolean, bool pivot stopped equals true, because we start off with it being true. So if the pivot is stopped, or the pivot rotor that is, then we want to turn it on. So pivot rotor, target RPM equals -1. That's because of the orientation of my rotor. I have to go in the negative direction to raise the solar panel. And since we have started our rotor, we can now tell our program that pivot stopped equals false, because it is no longer stopped, it is running. Now that our rotor is running, we want it to run in the right direction. So depending on whether we are increasing or decreasing in solar power, we want it to change direction if it is decreasing in the direction we're moving. So I'm going to make another if statement, but where I compare the solar power, but we need something to compare it to. So I'm going to make another variable up here called, let's use a double. A double is twice as big as a float, and a float is a floating point number. Floating point numbers are basically numbers that contain decimals. So if you want anything but a whole number like 1.1, then it needs to be a float or a double. So let's see, we're going to call that last output, and we're going to start that off by being 0. So if our panel's power output is less than the last output, then we're going to run a bunch of code to correct that. Or well, we're going to reverse the direction. So if that is true, then we want the rotor to move in the opposite direction of what it's currently moving. But it could already be reversed, so we don't want to just give it a static value like we're doing up here. So what I'm going to do is I'm going to say pivot rotor target RPM is equal to the negative, so I'm putting a minus here, negative of pivot rotor target RPM. So over here we're basically putting the target RPM, the negative of the target RPM into the target RPM. So we reverse direction. Right, so if the pivot is not aligned, then we start the motor if it is stopped. If not, we do nothing here. This will not be run. Then if the direction we are moving reduces the panel's output, then we're going to reverse direction. And then what? Now we need a way to tell if it's aligned. So basically we can assume that if we are reversing the direction, that means we were moving in the correct direction and we are now moving in the right direction. So I want another boolean to tell our program if we are moving in what I perceive as the right direction. So bool pivot the right way, and we're going to start that off as false because we are not doing that to begin with. So if pivot the right way, so if we are pivoting the right way but we have gotten to this point, then we have just reversed direction, so we are going the wrong way. But since we were pivoting the right way and just reversed direction, that might also mean we have crossed the peak power. So at this point we should turn off the motor. We seem to be aligned. So let's just start out by saying that pivot the line equals true because we are where we want to be. We want to stop the pivot rotor. 0. We want to say that the pivot is stopped because we just stopped it. And then we want to have a way of telling our code that we are pivoting the right way. So again, if we are moving in the wrong direction, we're going to reverse direction. And if we are moving the right way, we're not going to change direction until we are crossing the optimal point. So if we are reversing direction and we are not yet moving the right way, we were not moving the right way, we must be moving the right way now. So to append this if statement, I can put something called an else on it. Else and the curly brackets again. That basically means if this is not true, then we run this code. So if we are changing direction, but we are not pivoting the right, we were not pivoting the right way, that means we must be pivoting the right way now. So pivot the right way equals true. And next loop around, next time we change direction, we must have crossed the optimal point again. So pivot the right way is true, and we're going to turn everything off. Lastly, we want to do something, well, lastly for this first part at least, we want to stuff that something into that last output part there, because otherwise it will always be 0. So at the end of our code, we want to update that. Now, if you look out here, you can see some lines down. They basically means where this if statement starts and this is where it ends. So outside this if statement, we want to update that. So I'm just gonna say last output equals panel dot max output. So next loop around, the code will know through this what the panel power was during the last loop around. Now the problem here is that if we want to execute this code, well, if we want to use this code, we're gonna have to press run every single time we want to do it. So pressing run 10 times a second is gonna suck and not very automatic. So we are gonna add a line that is gonna make our code run itself. And to do that, we are gonna do runtime update frequency equals update frequency dot and then one of these options. The first one, none, is the default one. It just means that the code runs as it usually does. The next one, called once, means that when you first input the code into the programmable block, it will run all the code once, and then stop and only run when you say run. Next three ones are the interesting ones. Update 1 makes the code run by itself every 1 tick. 1 second in the game is 60 ticks, so that's 60 times per second. Next one, you guessed it, every 10 ticks, so 6 times a second. The last one is every 100 ticks, and that is about 1.7 seconds between each run. And that is also the update frequency of the solar panel in regards to its power output, which is extremely annoying, but it is what it is. So if we are just going to use this one solar panel, we could just use update 100. But I want to expand on this later, so we're going to stick with update 1. And there we go. Now our pivoting should work. It should pivot itself towards the sun. And let's go try it out before we continue our code. That's also generally a good idea. Try out your code every so often just to make sure you haven't broken something. Right, so let's go over there. All right, let's see if it works. So we're just going to put it into the programmable block and check if the code checks out. It does, and there goes the solar panel. So it should reset when it overshoots the best position and then hopefully align right in the middle. There we go. Stop. It overshoots a little bit, but that's because of the rate of the solar panel. So what we have made works. Right, let's move on. Alright, so that worked. Now we gotta add for the second rotor, and that's basically a copy paste of this, so I will just do that. Alright, so it is, as you can see, basically a copy paste with the names changed, of course, and I added the booleans for that as well. There has been two changes though. One is these ampersands here. That basically means and. Well, it means and. So the if statement is changed to if this is true and this is true, or in this case false because of the exclamation mark. So if these two statements evaluate as true, then we do the code. I have also added this little part here that says last output to 0 when we're done aligning. That is basically because the sun continues to move, so if we don't do that, it may have risen a little bit, gotten in a little bit better position before we start aligning the next one, and it can, well, weird things out. So I'm just setting it to 0 after we're done aligning. Now we should actually be able to align both things. I'm just going to add one more part to this code, and that is, well, basically when we're done aligning, it's going to stay still forever. It's not going to align again. It's kind of useless with a self-aligning solar panel if it only aligns one and never follows the sun. So I am going to make an if statement here that says if pivot is aligned and rotor is aligned and the output of the panel has changed by something. So panel max output. Now we're going to need something to compare that to. Oh yeah, I also added, I'm sorry about that, also added pivot aligned false in the second one here. I've done that because once the panel has rotated, the pivot position may no longer actually be aligned. So I want to do a quick alignment again. But I'm only going to do half of it. I'm not going to set pivot right way false, so we're only going to run it once instead of twice. But since this is the last part of the code that is run right here, we are going to set last output to be, no, sorry, because we already used last, so let's call final. Let's make a double call final output. Right, so the final output here when we are done aligning is equal to the panel max output. So we get what the output of the panel was when we were done aligning. So if the panel's output is now less than that, and let's say 90% of that, so I'm going to multiply it by 0.9 because otherwise the second if it gets like a fraction of a watt below, it's going to align again. It's going to continuously align. We could want that, but I don't want that. But yeah, so in that case, if we are pivot aligned, we are rotational aligned, and power has dropped by 10%, then we need to align again. Since all of our stuff up here is controlled by these booleans, all we got to do is set the booleans to false, and it will start all over again. So I'm going to say pivot aligned equals false, rotational aligned equals false, right way of both are false because we are not going in the right direction. Rot right way equals false. Well, that is it. Why is that not? Oh, it's working. Right, so now we should have all the code we need to make a solar panel align completely by itself. So let's test that out. Alright, and let's input the code again. Check the code, it works. Okay, it is aligning on the pivot first. I'm really beginning to wonder if I'm using that word correctly. But yeah. And stop. I was moving in the wrong direction. It sees that, it moves in the right direction, and it stopped, and it's just doing a quick alignment of that. There we go. And now it's done aligning. So if we then move the sun a bit, it should register that, and it does. So it will align again. Yeah, I'm sorry for the tedium, but it is a good example, I think. Right, so that'll keep aligning. Great. Now, what if we want to do the same thing, but with 2 solar panels? We could copy the whole code for each panel and yeah, bore ourselves to death. It's never fun writing the same thing twice, I think. So let's do that in a bit of a different way. Right, so this is an excellent example of slaving between rotors. So instead of doing all of this one more time, we can just make a small addition and make the second solar panel work. So I'm just gonna pop in the blocks we're gonna be manipulating. There we go. So I've called them slave pivot and slave rot. That is because they are gonna be slaving off the rotors on the main solar panel. So instead of writing a bunch of code, we're just gonna make a small addition down here at the bottom. So if pivot aligned and rot aligned, so if the main solar panel is aligned, then we are gonna say that slave rotors, slave rot target velocity in radians, that is the important part, equals the base rotor angle, so the base of the main solar panel, because and that's why the red is important, because this is read out in radians instead of degrees. You can do some math to convert that, but yeah, minus the angle of the slave rotor. So basically we're going to set the speed of the base rotor to be the difference in the angle. So when the difference is 0, the speed is 0. When the difference is big, the speed will be great. And we're going to do the same for the pivot. Alright, that's it. That's all we need to get the second solar panel to work. So let's check it out. Alright, let's pop the code in. So we should see an alignment like with the first solar panel of the, well, front, well, oh, sorry about that. So it's gonna align. Here you can also see the thing I mentioned about the weird angle of the vertical alignment initially. Once it's aligned, the one-on-one should follow suit. There we go. Also, that looked a lot better. So basically it will clone the angle of the first solar panel, not having to do any of the calculations or anything like that. So that part's pretty easy. Now, what if we, instead of adding one more, want to add the 32 more? Obviously, well, we could do the same thing 32 times, but there is a way easier way of doing that. So let's do that. Right, so as with adding another solar panel, adding 32 more is actually quite easy. What we're going to do is we're going to use groups. I've grouped all the base rotors of the additional solar panels and all the pivots into two separate groups. And we're going to add them, the groups, to our code using something called lists. So I'm going to make a list here where I do list, then brackets here. I'm not sure what these are called actually. But inside these brackets we're going to have to indicate what is going to be contained in the lists. And that's going to be my terminal block, because I haven't been able to get it to work with anything else than that. But that is basically a group of blocks that contains all the blocks. And I'm going to call the first one pivots, because that's what it's going to be. So the thing that makes making a list different from, well, one of the things at least from an object like this is you have to, instead of just doing my terminal block list pivots, I have to make it equal to a new list and end off with a parenthesis. So that is basically a way of creating this new list. And we're going to do that one more time with the rotors, or the base rotors. So I'm going to do that again and call that bases. Right, now we have our lists. They are empty and void, so we're going to have to stuff something into that. How we're going to do that is we're going to declare, we're going to get a group in the same way we get the blocks, basically. So I am going to make a new group, and I'm going to make it inside this because we don't actually need the group. We're going to use the group to stuff the blocks of that group into our list. So I'm going to make a new group here called IMyBlock group. There we go, IMyBlock group, and let's just call it Rotor group. And that is equal to grid terminal system get block group with name. Instead of block, it's block group. And I believe I called the block group pivots. And we are not gonna put any as or anything on the end of that. So now we have a block group, and inside that we have all the blocks in the group pivots. So what I want to do now is I'm going to stuff all those blocks into the list I created before. To do that, we are going to take the rotor group, get blocks, and parentheses. Now this works a bit counterintuitively. Let's just put pivots there. What this does is that it gets all the blocks from the rotor group and stuffs it into whatever you put in here. Well, in the list, basically. So yeah, it's a bit the reverse, but basically what we've done is we're taking all the blocks in the group, pivots, stuffed it into the list called pivots. And now we're going to do the same for the other one. We can reuse the group up here, so it's already declared, using IMyBlock group over here. So we can do rotor group is equal to grid terminal system get block group with name bases, and then stuff that into the other list. So rotor group get blocks and bases. Alright, this was basically the difficult part of this. So now we gotta manipulate all these, and to do that we're gonna use the for statement. Let's go down here where we're manipulating the other one. So a for statement is a bit more complex than an if statement, but not really. Let's just make it inside here. So a basic for statement looks like this: for int I equals 0. This is int I is this. It's an integer. It's a whole number we use to count up. So we're declaring that it's the data type int. It's called I. It could be anything, and it starts off at 0. This is our starting point. Then we're gonna do a semicolon, and then we're gonna set our evaluation. So for as long as I is less than something, in this case it could also be greater or whatever. It's like a for statement here in the middle. So while I is less than the number of blocks in our group is what we really want. So say pivots dot count. That's the great thing about lists. You can get pivots dot count. So a list dot count gets the number of blocks inside that group, that list. And then we need another semicolon, and that is basically what we're gonna do. So we're gonna start off by having that as a starting point. For as long as this is true, we're gonna keep going, and while we're going, every time we loop through our code, we're gonna do something. In this case, we're gonna say I plus plus. That means that every time we hit this for, every time the for loop goes through its code, it's gonna increment I by 1. And then as with the if statement, we're gonna end off with a double bracket. So just to really cut it out, for statement will run this code for as long as this is true. And every time it loops through the code, it will do this. If we didn't do this, then it will keep running forever, because I would always be less than the amount of blocks in the group. Right. So we are basically gonna copy this into our for statement, because we're gonna keep doing that. But instead of having slave rotor being equal to that one rotor up here, we are gonna give it a new life. So we're gonna delete that part. And then we are gonna make slave rotor equal to basis I. So it's gonna give us an issue here, because we are trying to put an IMyTerminal block into what is a rotor, and they're not the same data type, so it's gonna complain. Here we can use something called casting. Casting basically is for when you have one data type and you want to stuff another data type into it, and you're sure it's going to fit, but the program just won't let you. So I want this IMyTerminal block to be of the type IMyMotorStater. So I'm going to copy that. Then I'm going to make a parenthesis, and that casts that base to be treated as this data type. So what we've done now is, the first time this runs through, I is 0, so we're going to take basis 0. As I mentioned in the last video, programming usually starts counting at 0. So this will be the first block in our list that is going to be stuffed into slave rotor. And since both our groups are equally long, they are the exact same amount of blocks in each, we can just do the same with the other group inside the same for statement here. If they were of different sizes, you would have to make a for loop for each of them. But let's do slave pivot equals, and then let's do our casting again, pivots I. And that's it. We're done. Every time it gets to this, it will loop through all of them and apply the same action as we did to the second solar panel before, to each of those solar panels. That also means you could build another solar panel, add it to the group, and it will run without you having to touch the code at all. So yeah, let's plug it in and see if it works. All right. And check the code, it's all good. Okay, good. Now the pilot solar panel is gonna align, or at least attempt to align. And that's the wrong way, buddy. There we go. And there we go. All the solar panels align just fine. And we could double this, triple this, quadruple it, whatever, and it should probably still work. So that is it. This became a much longer video than I anticipated. I hope it helped give some insight into, of course, what an if and for statement is, how you manipulate a block group, but also was a good example of stuff you can use them for and ways you can use them with booleans especially. Yeah, as usual with these videos, I would really like some feedback. Just let it rip. But yeah, if you made it this far, thank you for watching, and see ya.